Hello people, welcome to another section of the continuous video series for trigonometry. So I was having a rethink of how much I wanted to do in trigonometry, and I looked at it and I was like, it's too fast. So many things, so I'll have to cut down most of it, or a good portion of it. The truth is, I've already done most of the important parts of trigonometry. I just have to finish one more part, which is half and double angle identities, as well as supplementary angle identity. I'll first do two questions there, but that's not what I want to say. So if I do that, I'm literally done with standard trigonometry. The other ones I was trying to include are not necessary, but as far as trigonometry is concerned, I just have 2 or 3 more things to talk about. As far as standard trigonometry is concerned, so yeah. The other ones are just, me trying to expand trigonometry. Perhaps when I finish complex numbers, probably will do more of that, maybe, if there's time. But if I finish supplementary angle identity, that's all for trigonometry for a normal state, for a normal standard, so to say. Because I wanted to talk about the inverse graphs, but the only thing I'll do that's kind of outside, it's not outside trigonometry, but the rest of the video is probably going to be, applications of these things and what we know, the identities we know, and how to apply them. And well, it's obviously physics. So yeah. So today we're going to start from 2 questions. Then I'll go into the meat of today's topic. So okay. Just need to set this properly first. Yeah. Okay, let's start. So the first question for today is going to be proofs show that one part of the equation is equal to the other part from whichever method I probably can do it. So the first one is going to be show that sine theta plus cosine theta squared plus sine theta minus cosine theta all squared is equal to 2. Right. So there are 2 ways we can go about doing this question. We can say, call this whole part A, and call this whole part B. And then we have A squared plus B squared equal to. But the identities we know about A squared plus B squared is as follows. We know that A squared plus B squared is equal to A plus B all squared minus 2AB. And also A squared plus B squared is equal to A minus B all squared plus 2AB. Right, so these are the identities we from algebra. We know that's correct. But if I'm doing binomial series, I would have to derive this, and then you can from there proof for your own A cubed plus B cubed, or A to the n for any general power of n where n is greater than 1. And then of just quick quantities, it can be continued with x.1 or something like that. So yeah. So you know these identities, but this is tedious. This is for your own, for your own interest, so to say. So you call this whole thing A because you have very large brackets and start simplifying. But for the sake of simplicity, there is no point of doing that because we know what we know what a plus b all squared is, and we know what a minus b all squared is. If you take this here, we have a feeling for what that is. If you take this here, we have a feeling for what that is. So sine theta as a here, and cosine theta as b here. So using this identity, so we're not using this whole thing as a anymore. But if you wanted to, you can actually, mathematics works out to be the same thing. Using this identity, we can say that since we know what a plus b all squared is, we can put that into the equation and take this negative to a to this part of the equation. So a sine theta and b is cosine. So we have, let me draw that, this to be equal to sine squared theta plus cosine squared theta plus 2ab sine theta cos theta. Right? So that's one part of the equation. Since it's a positive sign, we do not have to be too careful. Plus sine squared theta plus cosine squared theta. Hope it's not too long. Minus, this comes here, minus 2 sine theta cos theta. Okay, at this point I have to look at my camera resolution to see how far I can write. It's okay actually. It's all good. If we simplify, we already know what this identity is. This turns out to be 1. This turns out to be 1. And this one cancels this one. So we've actually proven that, well, that's equal to that. This whole thing is equal to 2. So that's a fairly, it's doable. That's a word. It's a doable question. Like doesn't involve any changing the sign to cosec or changing the sign to anything. So it's a straightforward thing. Just expand the bracket, you have the same thing. If you want to be more rigorous, you can, which is actually, to be honest, it's more, if you do things more rigorously, you tend to understand it more than the simplified version. If you use more rigorous styles, it's not that this is too rigorous, but if you wanted more expanded brackets and so on and so forth, you can call this whole thing A, you can call this whole thing B, and say, where is it? A squared plus B squared. I say A plus B, add these two together. So you have 2 sine theta. So you have, this is A, this is B, so you add both of them together. If you add both of these together, you have 2 sine, and cosine goes away. So you have 2 sine theta, all squared minus 2, and you can do all that on your own, it's not too hard really. But I'm not going to go off that. The next question goes as follows. It goes as, show that. Show that, or prove that 1 minus sine theta divided by 1 plus sine theta is equal to sec theta minus tan theta all squared. How do we go about, give me a second, because bear with me, I have to be very careful about my camera resolution, so I don't write past. Okay, yeah, it's all good. Okay, so I wish I could just take this away. So this is what we're trying to solve here. I do not want to do it. I do not want to deal with square roots. So I won't take the square here and turn it to a square root here. So what can I do? The only thing I can do, follow. right and tan. This is what I can do. So what's the idea? What's the idea? The idea is that I want to turn, because the left-hand side of the equation is in terms of only sign. So I want to turn every single part of this equation, the right-hand side, to signs as well. Well, this is the cosine, but let's go on. So we have sec theta. You know, we can actually do this the way we did this one and expand the bracket, but let's not do that yet. We'll do that later. Or let's just evaluate what sec theta minus tan theta is first. We have that to be, do the LCM, common LCM, that's equals 1 minus sine theta divided by cosine theta. So if you square them, you have square the numerator first. So you have, so this is how I want to do. I want to write the trigonometric functions first in order of the highest polynomials. In order of, how do I say it? Of descending polynomials. So I'll write sine squared theta first. Minus 2 sine theta plus 1 cosine squared theta. But I want everything in terms of sine, so I can further write this to be sine squared theta minus 2 sine theta plus 1 divided by 1 minus sine squared theta. How do I get 1 minus sine squared theta? I know that sine squared theta plus cosine squared theta is equal to 1. Therefore, cosine squared theta is equal to 1 minus sine squared theta. This is just by the way. Okay. But still, we're not getting anything good. The highest we're not really getting anything good. The highest we can do is simplify this to become sine theta. Wait a second. Okay. The highest we can do is say there's a sine theta into bracket sine theta minus 2. You can actually do that because there's a 1 there. You can. Or you can do, minus 2 plus cosec theta all divided by 1 minus sine squared theta. Okay, so this is as far as we can actually go. There's really nothing else we can do to simplify this so that we get something of this sort. But let's say we expanded this, we would have, so this didn't work, we didn't get anything. Well, there could be someone clever who could actually do this and simplify it such that we get this. But the problem is, we already have the denominator as something 1 plus something sine, 1 plus sine squared theta, even though it's not just possible to get a positive there. If you force the equation to get a positive there, you have a negative 1 there. Still doesn't work. But let's say we expand that term, we would have sec squared theta plus tan squared theta plus 2. Let me write sec first. Sec theta tan theta. And we know sec is, well, I've already written that here. And we know sec squared theta is equal to 1 plus tan squared theta, so we have I'm not going to do every step, so straight to the point goes 2 times square theta plus 2, sorry, minus 2 sec theta tan that plus 1. And if we want everything in terms of sine, we have that 2 sine square theta. We're still not going to get anything. I've already seen that. Another cosine square theta minus, yeah, we're not getting anything. Minus 2, got a 2, yeah, 2 sine theta divided by cosine square theta. I hope you can see where the cosine square theta is coming from. It's coming from the fact that, I'm just going to write this as 1 divided by 1 so we can do the LCM. It's coming from the fact that sec is one of cosine and tan is sine divided by cosine. So the denominators multiply and the numerators multiply. So we have 2 sine, 2 times 1, 2 times 1, 1 is from the secant. So we have 2 times 1 times sine, that's 2 sine, divided by cosine squared. So without wasting much time, so the denominator is cosine squared theta. And while we're not getting anything else, we're literally getting the same thing, but there's a little difference. Okay, so we have 2 sine squared theta here, minus 2 sine theta plus cosine squared theta. Now this is interesting. This method I have used, let's first change everything to sine. You see what I'm talking about? Okay, so this was interesting. We had that. Let's first turn this to a sine. So we have 2 sine squared theta minus 2 sine theta plus cosine squared theta plus cosine divided by 1. But we want everything in terms of sine, right? Okay, but yeah, just bear with me. I'll just write this as sine first, plus 1 minus sine squared theta. Divided by 1 minus sine squared theta. And that's equal to what? That's equal to, let me look at something first. That's equal to minus, so we have sine squared theta minus 2 sine squared, so not squared, sine theta plus 1 divided by 1 minus. We're actually getting the same thing. Okay, so we're getting the same thing as we got here, right? But there's something about this step that actually tells us something about the question as well. Oh, what's that? The thing is, if we took this, okay, let's equate them together because this is equal to this. This is just a simplified version. So if you equate this to this, well, and this is equal to this, literally the same thing. So we have 2 sine squared minus 2 sine theta plus cosine squared theta. And I'll leave the denominator as 1 minus sine squared theta. Is equal to where is it? Sine squared theta minus 2 plus 1. Okay, there's something called idempotence rule. Idempotence rule is where you have something like ax plus by plus c is equal to 3x plus half of y minus 2. And you're asked to find a, b, and c. It's literally there. A is equal to 3. So you're interpolating, I don't know if it's the right word, interpolating, but it's called the method of, interpolation for something else. It's the rule of idempotency. So this is the potent, I don't know how it's called, but yeah, I think you get the point. A is equal to 3 because they have the same variables, and B is equal to half, and C is equal to -2. So that's the idea I'm using. And I mean, you can actually solve for it to see that it's true. So this can be further written as, so if you cross multiply this and this, you see that these cancel. This cancels this. This cancels this. But from the rule of idempotency, mistake. So from the rules of idempotency, this cancels this, but 2 sine squared theta is equal to sine squared theta, and cosine squared theta is equal to 1, which is interesting. It doesn't give you an answer, but it tells you something about the question. It helps you verify that this is true. How does it help you verify? See, ladies and gentlemen, 2 can never be equal to 1, okay? So it has to be a function of the angles that make this equation to be true. 2 can never be equal to 1. By that I mean you can't cancel this and cancel this and say 2 equal 1. It's not possible. So it has to be a function of the angles that makes this equation true. And we will actually verify this with this. Because we can solve this equation and get the answer for the angle and put it here. I said that's true. I could use that to verify that this is true. It doesn't give you an answer, but it gives you a method of verification. Therefore, what I'm trying to say is everything I've done so far is a method of verification, not of proof. It's a method of verification to show that this is actually correct. But we haven't actually shown that the left-hand side is equal to the right-hand side, or the right-hand side is equal to the left-hand side by any sort of simplification or magic trick or mathematical trick, whatever. Anyway, so if we solve for this, we have cosine theta is equal to 1 still, and theta, the only place where cosine is ever positive is 0 degrees and 360 degrees. So yeah, theta is equal to 0. And if you plug 0 in here, into 2 sine squared theta equal sine squared theta, you see that sine is 0 at 0 degrees. And for the sake of verification, to verify that 1 minus sine theta divided by 1 plus sine theta equals sec theta minus tan theta all squared, we can say that sec theta is, what's sec theta? Sec theta is equal to 1 divided by cosine theta, right? And if that's true, and we know what cosine theta is, we know cosine theta is equal to 1, cos theta is equal to 0. So 1 divided by 1, that's 1, and tan theta is equal to tan theta is equal to sine 0 divided by cosine 0, and that gives you 0. Hence, put that here. You have 1 minus sine 0 divided by 1 plus sine 0 is equal to 1 minus 0 all squared. And you see that's true. So the method that I have method of simplification that I have just used actually shows that the equation is correct. Now the whole essence of this is actually prove that this equals this. And yeah, it's kind of, a stabbing you, it's pinching you that upon all the whole simplification, you're not getting anything like it. Because it's quite annoying, because you're getting minuses at the denominator. Look at what that is. What can we actually do? One thing I know I can do is assign a variable. I can say that 1 minus sine theta is equal to u. And if that's the case, sine theta is equal to 1 minus u. Right? So that's true. Hence, 1 plus sine theta is equal to 1 plus 1 minus u. And that's equal to 2 minus u. So 1 minus sine theta divided by 1 plus sine theta is equal to 1 minus, u divided by 2 minus u. Now, what's the question? The question has changed. It's kind of like a Jacobian, but it's not really a Jacobian. The idea, what's the idea now? What are we trying to do? We're trying to solve the right-hand side equation so that we simplify and get this. It's quite easier now because we have just one term at the numerator and still one variable at the denominator. So like a Jacobian, just think of it. I don't know who knows about Jacobian. Jacobian vectors or Jacobian constant, whatever it's called. It's how you change axes or variables. You know how you do say, I don't know, like basic integration of say e to the x, or which one will I use now? Let's say x, and for a simple function, say x squared plus 1 times x. This is a simplified version. What you could do is say u equal to x squared plus 1. So this is actually called a Jacobian, or what's it normally called? It's just like changing the variables from u to x to u. So what a Jacobian does, it changes the axes of integration or axes of a given equation to a different set of axes so that the equation becomes simpler to solve. And then hence you can solve this, or you can just multiply all through and do the integration. But this is actually called a Jacobian. But in one dimension, the Jacobian just goes straight up. But if you do like for 2 dimensions, let's say a double integral of some function. A double integral of some, let's say a polar function. So we have f of x, y, where x and y be by polar equations. So r dr d theta, r dr d theta. This r is called a Jacobian as well. Okay, so this is normally here. That's how it works. But if you think about it, it's like you're multiplying 3 infinitesimals. If you see it for the first time and you understand math, it looks like you're multiplying 3 infinitesimals, but in 3 dimensions, and that doesn't make any sense. But you see that this is not actually infinitesimal. It's a constant, or it's Jacobian. That's actually derived from the basics of whatever this is, double integrals. But we're not doing that really. How did I forget from here to Jacobian? So So we want to solve the my equation. Where did I drop it? Did I just remove that? Right. 1 minus sine theta divided by 1 plus sine theta is equal to u divided by 2 minus u. So we want to solve for sec and tan first before we start simplification. So we know sec theta is equal to 1 divided by cosine theta. But first, we don't know what cosine is. So we're going to use the thing, what's it called? Trigonometric identities. So we know, I'm not going to write such, I'm not going to just keep on writing sine squared theta plus cosine theta equal 1. We already know that. So we know cosine squared theta is equal to 1 minus sine squared theta. And that's equal to 1 minus u all squared. Careful about the brackets. This is minus multiplying everything, but you don't do the minus first, you do the bracket first. So you have 1 minus, so write u squared plus minus 2u plus 1. So if you introduce the brackets, if you open the brackets, you have, so 1, I'm not going to write the 1 because you see it's going to cancel out. So you have minus u squared plus 2u. So you have 2u minus u squared minus 1 and plus this one. So that goes to 0. That's the value of cosine squared theta. So to get cosine, is the square root of that. So that's cosine. Okay, so that's that for that. So if you do it for sec, theta is equal to 1 divided by square root of 2u minus u squared. Right. Let me take a look at my camera first. Everything's going well so far. Okay. Back to work. So, tan theta is equal to 1 minus u divided by what? Cosine. So that's cosine is that square root of 2u minus u squared. Yeah. So sec theta minus tan theta is equal to 1 divided by square root of 2 u minus u squared minus 1 minus u divided by minus that, so that'll be just u, right? So square that. U squared divided by the square of the square root, so you have 2u minus u squared. Well, you have an answer, don't you? If you can already see that it's correct with this, because if you simplify further, you have u divided by 2 minus u, and that's equal to this. So that's the solution. So that's the solution to this question. Yeah, so that's the solution to this question. There's some more tricky ones. So, well, this is give you a run of your money for your money, whatever. So yeah, that's that for today. So still take a glance at it, and then I'll start doing the main thing for today. Yep. So the main work of today, I don't know where to start from. I guess I'll start from something because it's not It's just straight to the point. So okay. Yeah, okay. I think that's all right. Okay. Two angles are supplementary if the sum of those angles are equal to, well, it's not necessarily two angles. For any n number of angles, if it's the case that they're all supplementary, then the sum of n angles is equal to 180. I don't know if I should write that, it's too tiring to write really. For any n number of angles, if they are supplementary, therefore, the sum of all the angles are equal to 180, or is equal to 180, sorry, I think that's the right verbiage. It's equal to 180. Take the case study of two angles. If x and y are supplementary, then this statement of this equation is true for both of them. It's true for x plus y is equal to 180. And if you just stare at it for a bit, try to see what's happening. The maximum value for x and y, for x or y, is 180. Right? Just think of it. The highest number x can be where y will be insignificant is 180, in which case y will be 0. Or if x is 90, it's guaranteed that y is 90. It can't be anything other than 90. It's a simple equation, because if you solve for x, you see that whatever y is dependent on the value of x. So whatever x is dependent on the value of y. Okay. So x plus y is equal to 180. So if x is not 90, then y cannot be 90. So the only case that we know what the two equations are, what the two variables are, if one of them is going to be 90, in which case the other one is 90. Or if they're not supplementary, then you cannot be so certain to give such a definitive answer. So if x and y, if either one of them is not 90, in which case you know what the other one is, they have to do something else. One will be less than 90, and the other will be greater than 90, or the other one will be less than 90, and the other follows vice versa. So x equal to 180 minus y. So let's do some trigonometric identities with this thing and see where we're going. So if I say sine of x, sine of x is equal to sine 180 minus y, and really you can see that it's going to be a positive number because, well, if you think about it very with analysis, you can think of the case scenarios. That's what I mean by analysis. If you say you don't know what x is, well, okay, let's start from this. Sine x is 180 minus y. I know that this is positive. How do I know this is positive? Well, let's see. If y is, let's say, if x and y are they're not 90, therefore they can be anything. So let's assume the case that x is greater than y. If x is greater than y, Therefore, y will be a small number